Hello, and welcome to this video on joints and welds. To begin with, let me start by sharing the screen so you can follow along with the PowerPoint that I'm going to share. My name is Girish Kelkar, and I am a welding consultant operating as WJM Technologies. Additional information on my consulting business is on the web at welding-consultant.com. If you're new to the topic of welding, I would recommend that you review some of these other videos which I've already posted on this playlist so that you have a better understanding of this video about joints and welds. And those include weld section analysis, fillet weld measurement, bonds and resistance welding, projection welding, and laser beam quality. They are in different playlists, including metallurgy, arc welding, resistance welding, and laser welding. There are basically 5 types of joints: a butt joint, lap joint, T-joint, edge, and corner. Most joints can be used for soldering and brazing as well. However, lap joints are the most common for soldering and brazing. Now let's review what is the difference between joints and welds. The schematic on the left shows a T-joint. As the name implies, it is formed by 2 components coming as a T. And this dark line is shown as the interface. Now, this is a line, but in reality, it's going to be a plane in a 3-dimension. You can take the 2 T-joints. You can take a T-joint and make what is called a fillet weld. A fillet weld is a weld where you add material which is mostly on the outside. There is some fusion to the 2 components, but primarily the weld is on the outside, not much along the interface. Whereas you can also make a groove weld. A groove weld is where the weld is actually primarily along the interface and a little bit on the outside. So you can take a T-joint and make a fillet weld, and you can also take a T-joint and make a groove weld. So that is the distinction. A joint is just the arrangement of the parts. The joint is how the parts are coming together, whereas the weld is how the parts are going to be connected together. So that is the difference between the joint and a weld. Unfortunately, a lot of times the terms joint and weld are often used interchangeably, and that can cause some confusion. So one of the main things I would like you to remember from this video is this distinction between joints and welds. Let's look at a T-joint made with a fillet weld. So here's a T-joint. It's a cross section. This is one component. This is the other component. And this is the fillet, which is shown in section. If you're not familiar with weld sections, please review the video on weld section analysis in the metallurgy playlist, where I explain how these weld sections are made. By some estimates, fillet welds make up about 80% of all arc welds. So fillet welds are extremely popular. So if you're in the welding business, especially with arc welding, it is very likely that you have made some fillet welds. One of the benefits of fillet welds is it requires minimal penetration at the interface. It requires minimal preparation of the interface. And that is one of the reasons for its popularity. The other type of joint which is quite common is butt welding. Butt welding, as the name implies, the 2 parts are coming together and butting against each other. On the left, I'm showing a schematic of a square groove butt joint, where it's a square groove. By definition, that means that the edges are straight. So the parts are coming together as a straight edge. And the weld interface is from the top to the bottom over here. Square groove joints are common when the parts are fairly thin, especially for arc welding, and they are of the order of less than 1/4 of an inch, usually even less than 3 millimeters. With laser beam and electron beam welding, you can make square groove welds which are much thicker, up to 1 inch in laser welding for sure, and even multiple inches for electron beam welding. When you get a square groove design or any butt joint, one of the things you have to see on the part drawing is what exactly is the designer asking for. So they could be asking for a PJP, so partial joint penetration. That means you do not expect the weld to go through all the way. Or it could be a CJP, complete joint penetration. That means the entire interface has to be welded. When you weld the entire interface in a CJP, as I've shown in the schematic cross-section on the right, you are going to get some crown on the top and a root on the bottom. One thing to keep in mind is the crown and the root do not contribute to the strength of the weld. So even if you have extra material on the outsides, on both sides, that does not contribute to the strength of the weld. The strength of the weld is only related to the thickness of the component. One of the unique aspects of CJP groove weld is that once they are made with a suitable filler and they are 100% inspected, so there are no defects on the inside, they can get a 100% efficient rating. What that means is you can assume at that point is that the weld is as strong as the parent metal. CJP groove welds made in such way are the only joints which can get that 100% efficiency rating. All other joint designs will have less than 100% efficiency. And that fact has to be taken into consideration when the analysis is done for those welds. Here's an example of a CJP groove weld where we have two titanium plates which were butt welded together. It's a square groove, so there is no edge preparation, but you can see the crown which is formed on the top and a root on the bottom. This is made with a TIG welding with a filler wire. Even though we do need a crown and the root, there are limits to how big those things can be, how deep, how high up and how deep the crown and the root can go. We also need good tie-in on the toes. So it has to be a smooth transition from the fusion zone to the base metal at the toes. So there are a lot of requirements for crown and root, even though we do need it over there. Once the parts become so thick that a square groove design is not cannot be full have CJP weld in arc welding, then we have to use other designs where you allow a way for the filler wire to go in through the thickness. So this can include a single bevel, which is a bevel on just one side, a double bevel, which is again on the same component, but from both sides. We can have a single V, a double V, a single J, a double J, and a single U and a double U. So these are all designed used for arc welding, where you need to use the filler wire. The filler wire will essentially fill up this space. In some situations, depending on the joint design, you may have to make some of the weld from the top and then have access from the other side and make some passes from the other side as well. In situations where we are using laser welding, which is typically used in autogenous fashion, that means you're not adding a filler wire. We often use a butt joint with a shoulder design. A butt joint with a shoulder, one of the components has a step, a shoulder, and the other component mates with it. And then you can make the weld as shown in the cross-section on the right-hand side, which can be 100% penetration, 100% or more. In this case, 100% means through the thickness of the thinner component. The beauty of design with a shoulder is you can go beyond 100%, as I've shown over here in this section, and not worry about this molten metal dropping into the enclosure. A lot of times, laser welds are made for medical devices and electronic enclosures where we don't want the molten metal to drop inside because that can create trouble for the operation of that device. Another benefit of butt weld with a shoulder is the parts become self-aligning and self-fixturing. A lot of the parts which you are going to be eventually, if you make laser welds and medical devices and electronic packages, they're all getting smaller. And as the parts get small, it is very hard to hold both the parts. So what you do is the bigger of the part will have a shoulder and the smaller of the part will snap into place. And then you go and make the seam weld, which is a typical application for these designs. The other joint we are going to review is a lap joint. A lap joint is where two parts come together, one on top of each other, and you can see the interface over here. And it can be made in two ways. Using laser welding or electron beam welding, you can make a lap joint with a lap weld. That means the energy goes through the top part into the bottom part, and the edge is not disturbed over here. The beauty of this type of weld, it is very insensitive to misalignment. So you can have a little bit misalignment of the laser beam and it doesn't affect the welding quality as much because the length of the weld or the width of the weld at the interface does not change too much. Lap joints can be also made with fillet welding. It can be on one side or both sides. And this is very common with arc welding and laser welding. However, this type of weld is sensitive to misalignment. So you have to be very careful where the laser beam is coming or where the arc is coming or where the wire is being fed to make sure you make a weld which satisfies the requirements. Here are some examples of cross-sections of lap welds made with laser welding. On the left is a cross-section between two parts. The top part is very thin. The bottom part is obviously much thicker. On the right-hand side, we are seeing a sandwich. We have three components. The top and bottom are the same, and the middle one is a little bit different. So obviously, this is a dissimilar metal weld, and it is going through all the three layers. On the next slide, we see a lap joint made with a fillet weld. In this case, the cross-section shows over here. This is the fusion location, and the two parts have a gap in between. So that is one of the benefits of using a filler wire. The filler wire can compensate for the gaps, and even the edge preparation does not have to be perfect. So fillet weld in a lap joint can be made, especially in parts which are stamped and the edges are sheared, so nothing is absolutely perfect, and you can still make a good weld. And that is where a filler wire and GMAW come into play. So these welds are very common in automotive chassis assembly and frame assembly, where a lot of the components are indeed stamped and sheared, and they are not perfect. Resistance welds also are essentially lap welds. You can weld sheets together, or you can have a projection weld, and you can have a spot weld or a seam weld. And I have shown examples of weld sections in the video on resistance welding, so I'm not sharing those at this video over here. So feel free to review those videos to look at the cross sections. Another application for lap joints is soldering. This is a very common application. We can see the cross section shown over here. This is an electronic device, a alumina capacitor. This is a copper trace on a circuit board, and this is the fillet made with the solder. So you can see that the solder has formed an external fillet, and the solder has also gone between the two components in the solder lap location over here. Keep in mind that the strength of the solder connection is primarily from the lap location over here. The external fillet does not add much of strength, but gives you a visual indication that the solder did flow properly during the joining process. The fourth type of joint is a corner joint. A corner joint, as shown schematically over here on the left, and I'm showing you a laser beam coming down over here. That's how this particular joint was made in the cross section on the right. And you can have a corner joint being welded from the outside or the inside. And again, here you can have fillet welds on both sides or groove welds on both sides or either side. So there are choices. The fifth type of joint is an edge joint. Again, as shown in the schematic on the left, we have the laser beam coming down from the top and melting a pool of metal over here. This could be classified as a butt weld over here, but here again, you can make a weld on the inside as well. I'm showing you a cross section of a typical edge weld. Here you have to keep in mind that whichever way weld you're making, make sure you look at the design, because there are so many options for making the weld from different sides, different shapes, different profiles, that you want to go ahead and make sure that you are actually meeting the expectations set up in the part drawing. In summary, we have 5 different joint designs: butt joint, lap joint, T-joint, corner, and edge joint. Keep in mind that joint is just the arrangement of the parts, whereas weld is how the parts are connected. This is a common misunderstanding, and a lot of times the words joint and weld are used interchangeably, and that can create some confusion. So it's always a good idea to describe the weld as a type of weld in a type of joint. For example, you should say, we are making a fillet weld in a T-joint, or we are making a lap weld in a lap joint. So that will keep matters clear. A groove weld in a butt joint is common for thick sections, as we saw, and that does require a lot of careful machining and edge preparation. So groove welds are great for thicker components, but of course they need a lot of extra preparation. On the flip side, fillet welds are the easiest to make, and the reason probably why they are so popular is they require the least amount of edge preparation, and they can tolerate a lot of fit-up issues because we are going to add the filler wire, especially from the outside. And that makes it for a very robust weld under such circumstances. Okay. Well, thank you for your time. I hope you like this video on joints in welds. If you are interested in learning more about welding and joining, please subscribe to this YouTube channel by clicking on the subscribe button below. Not this button as shown on the screen, but there should be a similar button right below the screen where you can click and subscribe. There are many other videos on different topics on this channel, and so you can look at those videos, including playlists for metallurgy, arc welding, resistance welding, laser welding. And this particular video will be in the welding design playlist. I want to thank you for your time and wishing you the very best in your efforts to make a better weld. Take care.